The James Webb Space Telescope is perturbing the apple cart. Suddenly, we realize that we may have to rewrite every textbook dealing with the beginning of the cosmos. In their search to understand the first stars and galaxies that illuminated the universe, astronomers, still unsure but moving closer to one discovery at a time, find illumination. That is the incredible, immutable fact. The conclusion of the unparalleled James Webb Space Telescope's discoveries, marking its 10 billionth observation, closes its first year of observations with the purpose of glimpsing the faint infrared glow of the universe's earliest luminous objects. Webb's vision reached back into the first few 100 million years after the Big Bang, allowing it to acquire additional and better information on newly formed galaxies than any other facility yet built. But its baby photos from the Hall of Galactica have proved more bountiful than most researchers dared to dream. Candidate galaxies in the early universe are accumulating in numbers that defy predictions, with dozens found so far, and that liberates scientists. As Charlotte Mason, an astrophysicist at the University of Copenhagen, said, "We really hadn't anticipated this." For weeks and months following JWST's findings of surprisingly mature early galaxies, observers and theorists rushed to explain the numerous anomalous, big, and bright early galaxies. Could they be the result of errors in the analysis of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models? Or were they just the first indications that the universe is more bizarre and intricate than any of our daring theories had ever speculated? Was the Big Bang Theory wrong? Join us today as we dig deep into how the James Webb Space Telescope broke the universe. Let's get to the point. To understand the dilemma, let's go back to when the universe was believed to have been created. Following the Big Bang, the infant universe began to recede. A few million years later, the raging plasma that filled space settled down, and protons, neutrons, and electrons combined into atoms, mostly neutral hydrogen. Things were quiet and dark for a period of uncertain duration known as the cosmic Dark Ages. Then something happened. Most of the material that flew apart after the Big Bang is made of something called dark matter, but we can't see it. It exerted a powerful influence over the universe, particularly at first. In the conventional image of cold, dark matter, a term that means invisible or slow-moving particles, dark matter was flung about the cosmos indiscriminately. In some areas, its denser distribution occurred. In these regions, it began collapsing into clumps. Visible matter, meaning atoms, clustered around the dark matter clusters. As the atoms cooled off as well, they eventually condensed, and the first stars were born. These brand new radiation sources reionized the neutral hydrogen that filled the universe during what is known as the epoch of reionization. Through gravity, larger and more complex structures built up. Meanwhile, the vast cosmic web of galaxies kept flying apart. The universe was expanding quickly. Edwin Hubble, an astronomer, discovered in the 1920s that the universe is expanding. In the late 1990s, his namesake, the Hubble Space Telescope, found evidence that the expansion is accelerating. Think of the universe like a raisin loaf of bread. It starts as a mixture of flour, raisins, yeast, and water. When you use the yeast, these ingredients combine, the yeast begins respiring, and the loaf begins to rise. The raisins, standing for galaxies, stretch further apart from one another as the loaf expands. The Hubble Space Telescope observed the loaf rising even more quickly, with the raisins breaking apart at a rate that is beyond their attraction by gravity. This acceleration appears to be driven by the repulsive energy of space itself, so-called dark energy, which is symbolized by the Greek letter lambda, plug values for cold dark matter, regular matter, and radiation into the general equations of Albert Einstein's theory of relativity, and a model is created of how the universe evolves. This lambda cold dark matter, or lambda CDM model, corresponds to nearly all observations of the cosmos. 1. Way to test this picture is by looking at very distant galaxies, equivalent to looking back in time to the first few billion years following the enormous clap that began the universe. It was simpler then in every way, easier to compare with evolution predictions that were first made by astronomers. In 1995, the Hubble Space Telescope gathered 342 images in 10 days, exposures of an empty-looking patch of space in the Big Dipper. Astronomers were amazed by the abundance hidden in the pitch black. Hubble could see thousands of galaxies at different distances and various stages of development, going back much further than anyone predicted. Hubble would go on to find some exceedingly distant galaxies. In 2016, astronomers found its most distant one, referred to as GNZ11, a tiny speck that was around 400 million years old, surprisingly early for a galaxy after the Big Bang. This did not cast doubt on a portion of the Lambda CDM model because it was only 1% of the mass of the Milky Way and because it stood alone. Astronomers required a stronger telescope to see whether GNZ11 was an oddball or part of a larger number of early-stage puzzling galaxies that may assist in determining whether we are missing a crucial piece of the Lambda CDM recipe. The James Webb Space Telescope, also known as JWST, renowned for being the largest, strongest observatory to ever be launched, was constructed to change the way we think about the universe. At 1.5 million kilometers away from the influence of Earth and chilled close to absolute zero due to its tennis court-size sunshade, the telescope carries a massive mirror with segments and exquisitely sensitive instruments designed to uncover details of the cosmic dawn for the first time. That promise was kept. Within minutes and weeks after JWST's full operations, it exceeded astronomers' wildest dreams, seeing galaxies awe-inspiringly close to the dawn of time, probing the atmospheres of exoplanets in unheard-of depth, and providing stunning new views of worlds in our solar system. But it's just getting started. As Webb's vision reaches back to the first few billion years after the Big Bang, it makes it possible to obtain more and better data about newborn galaxies than any other facility. However, the stakes are nothing less than our comprehension of how the universe works. The well-ordered universe we know today, early revelations of the primordial chaos web, could edit the first few chapters of cosmic history. That goes beyond far-off galaxies and distant epochs, but additionally, our own existence in the familiarity with the Milky Way. As first scientist Mark McCaffrey, a senior advisor for space and space exploration in Europe, the agency said, "You don't make these machines to break the paradigm but confirm it. There is no telling how they will break. Researchers use a version of the Doppler effect to measure objects' distances. This is comparable to determining the location of a passing ambulance siren. The pitch of the siren is higher as it approaches and then lower as it recedes. As a galaxy gets further away from us, the faster it moves away, and so its light stretches to longer wavelengths. The magnitude of this redshift is expressed as Z, where Z has a particular value that tells you how long an object's light must have traveled to reach us." One of the first papers on JWST data, by MIT astronomer Naidu and his colleagues, whose search algorithm flagged a galaxy that appeared amazingly bright and unjustifiably far away, dubbed it Glass Z13, indicating its apparent distance at a 13-point redshift, further than anything seen before. The galaxy's redshift was later revised down to 12.4, and it was given the new name Glass Z12. Scientists working on a variety of sets of JWST observations were reporting redshift values from 11 to 20, with one galaxy called Sears 1749, or CR2Z17, whose light appears to have left it 13.7 billion years ago, just 220 million years after the Big Bang, a blink after the beginning of cosmic time itself. These putative detections suggested that the neat story known as Lambda CDM might be incomplete, somehow. The size of galaxies exploded right away in the early universe. You don't expect to see massive galaxies. They haven't had time to produce as many stars as they had, nor merge together. Chris Lovell asserted in a study released in November that analyzed computerized models of universes under the control of the Lambda CDM model and discovered that early bright galaxies were an order of magnitude heavier than the ones that formed concurrently in the simulations. Some astronomers and media outlets claimed that JWST broke cosmology, but not everyone was convinced. One problem is that the predictions made by Lambda CDM aren't always crystal clear. Whereas dark matter and dark energy are simple, visible matter has complex interactions and behaviors, and nobody knows exactly what went down in the first years, after the Big Bang. Those frenetic early times must be approximated through computer simulations. Another issue is that it is difficult to tell exactly how far away galaxies are now. In the months following the initial papers, some of the alleged high redshift galaxies have been rethought. Some were relegated to subsequent stages of cosmic evolution as a result of new telescope calibrations. For example, Sears 1749 is found in a region of the sky consisting of a group of galaxies whose light was emitted 12.4 billion years ago. Additionally, Naidu suggests that the galaxy is actually a member of this cluster, a closer intruder that could be filled with dust that makes it appear more red-shifted than it actually is. No matter how you look at it, Naidu's Sears 1749, far away as it is, would be a new type of galaxy that we were unaware of, a very low-mass, tiny galaxy that has somehow built up a lot of dust in it, which is something we traditionally do not expect. He suggested that these brand-new kinds of things that are hard to understand are for the very distant galaxies. The most definitive distance estimates would require JWST's most powerful capability. JWST not only observes starlight through photometry, also known as measuring brightness, but also through spectroscopy, or measuring a light's wavelengths. If a photometric observation is similar to a picture of a face in a crowd, then a spectroscopic observation is like a DNA test that can tell an individual's family history. Naidu and others who achieved early success utilizing galaxies' measured redshift brightness derived measurements primarily by observing faces in the crowd with a top-notch camera. That method is far from airtight. At a January meeting of the American Astronomical Society, astronomers quipped that maybe half of the early galaxies that were observed by photometry alone will turn out to be mismeasured. But early cosmologists announced in December that they had combined both methods for 4 galaxies. The JWST Advanced Deep Extragalactic Survey, or JADES team, searched for galaxies whose infrared light spectrum abruptly cuts off at an important wavelength, the Lyman break. This break takes place because hydrogen floating between galaxies in the void absorbs light. Because of the universe's unending expansion, like a rising raisin loaf, the light of distant galaxies is shifted so that when a break abruptly shifts, the light from the galaxy appears to fade at longer wavelengths, making it further away. With JADE's spectra, redshifts up to 13.2 were identified, which means that the galaxy's light was released 13.2 billion years ago. As soon as the data were retrieved, JADE researchers started to panic in a shared Slack group. Kevin Hainline, an astronomer at the University of Arizona, said, "It was like, oh my goodness, we did it." And he stated that these spectra are merely the beginning of what he believes will be astronomy-changing science. Brant Robertson, JADE's astronomer at the University of California, Santa Cruz, says the findings show that the early universe underwent rapid change. In its initial evolution, galaxies' evolution takes billions of years, 10 times quicker than they do today. It is comparable to the way a hummingbird is a tiny creature, but its heartbeat is so quick that it's living a life distinct from that of other organisms. The heartbeat of these galaxies is happening on a much more rapid timescale than something similar in size to the Milky Way. However, were their hearts beating too quickly for Lambda CDM to explain? Astronomers and the public gaped at JWST images. Behind the scenes, researchers began their work to determine whether the galaxies blinking in our view really depend upon lambda CDM or just help nail down the numbers we should plug into its equations. One significant but inadequately understood number concerns the masses of the earliest galaxies. Cosmologists attempt to determine their masses to tell whether they match lambda CDM's predicted timescale for the expansion of the galaxy. The mass of a galaxy is derived from its brightness, but Megan Donahue, an astrophysicist at Michigan State University, claims that the relationship between brightness and mass is an educated guess based on hypotheses derived from known stars and well-studied galaxies. One fundamental assumption is that stars always form within a specific statistical range of mass, known as the IMF, or initial mass function. This IMF parameter is extremely important for obtaining the mass of a galaxy from the brightness of its measurements because more light is produced by hot, heavy blue stars, despite the fact that most of a galaxy's mass is typically locked up in cool, red, small stars. But the IMF might have been different in the early universe. If so, JWST's early galaxies might not be as heavy, despite their brightness. They may be bright, but light.